Hello everybody, and welcome to the most interesting lecture you've ever heard. No, sorry, I'm joking. It's not going to be the most intellectually stimulating lecture or even at all interesting, but we have to get a grasp on how using statistics in psychology allows us to decide when we do research, whether it's descriptive, correlational, or experimental, to decide whether we actually have anything worthwhile, anything that tells us that whatever we're studying is meaningful. So statistics, as I'm sure you're aware, is a branch of math used by researchers in every area to organize large amounts of data and then somehow summarize it, aggregate it, and allow us to interpret it. If you were to have a survey with 20,000 people's answers, we could look at the raw data, but it would be relatively meaningless. We'd have a 1, 2, 5, yes, no, male, female, all kinds of data. Statistics allows us to take that data to, in some ways, aggregate it, put it together into meaningful pieces of information, which again, in some cases, allow us to make inferences about what all this data means. Now, there's two branches of statistics we use in psychology. The first is called descriptive statistics, and as the word indicates, these statistics describe the data. And a perfect example of that, which we'll talk about here in a second, are averages. I may have, again, 20,000 pieces of data, and as I look at them, I say, wow, very interesting. But if I all of a sudden have the average person that does this, or the average score for people in general psychology, the average, that is just a simple way in which we can take 20,000 scores and actually boil it down into one, and that gives us meaningful information about all 20,000 of those scores. So that's what we mean by descriptive statistics. Inferential statistics goes one step further. Again, as the word would imply, it allows us to make inferences, to make judgments about the data and what the data means. We particularly use inferential statistics when we're trying to compare 2 or 3 or 4 sets of data or 4 groups to see if there are, for instance, differences between those groups on this, that, or the other thing. So this is how we use statistics. Very often, we want to also take our statistics and present them in visual form. I don't know about you, but I like a picture because, to me, a picture is worth 1,000 words. And if I can visually see something, it's easier to grasp it than sometimes just the words or just the description. So we use statistics just to help us have a better grasp of what we're doing in psychology. Now, this descriptive data allows us to take, again, to make all kinds of observations and then how to describe it. So let's take this example. How many hours do you exercise each week? That's might be kind of interesting. And so let's say that we got a bunch of people and we asked them how many hours they exercised each week. So imagine that we had 30 people and we asked everybody, estimate how many hours of exercise you engage in each week. And the lowest number we got was 0. And the highest number we got was 7. So a frequency distribution or a frequency distribution table looks like what's right in front of you. We would take the possibilities, 0, 1, 2, 3, 4, 5, 6, and 7, and then we would take the frequency. So 4 of our 30 people didn't exercise at all. 7 exercise 1 hour on average a week. 8 exercise 2 hours, and so on. Only 1 person exercises 6 hours a week, and then only 1 person exercises 7 hours a week. Now, this is a visual kind of summary of the data. This is a little easier to understand than if we just had all the numbers, all 30 numbers. placed on a piece of paper in front of us. So the most simple descriptive statistics would be a frequency distribution, what you have in front of you. But even this can be a little confusing. It's a little hard to read. So we might want to take this information and represent it in what we call a histogram or a bar graph. And you can see here that on the left, in the y-axis, we have the frequency from the lowest to the highest, and in this case, 0 and 8. And then on the bottom, we have the number of hours that are possible, so that would be 0 to 7. And you can see here that we have a quick picture that 4 people exercise 0 hours, 7 people exercise 1 hour, 8 people exercise 2 hours, and so on and so forth. And so a histogram gives us, again, an even better picture of describing this group of 30 people. Another variation on this would be what we call a frequency polygon. And instead of representing the data as bars, we simply connect the pieces of data into a continuous line. Now, why would we use a frequency distribution over a histogram? Well, it's a little more accurate, actually, because if we ask someone, so for instance, the 8 people that exercise 2 hours a week, did all 8 of those people exercise exactly 2 hours a week? No. Some of them maybe an hour and 50 minutes, maybe someone else an hour and 56 minutes, someone else 2 hours and 2 minutes, another person 2 hours and 4 minutes. In other words, the number 2 hours doesn't represent just 2 hours exactly, but it represents a little less and a little more. And so a frequency polygon pretty much accurately represents the fact that there are, each of our whole numbers really represents on either side of it, some a little bit less and some a little bit more. And for what it's worth, a frequency polygon always starts with 0 and always ends at the bottom. Because it simply has to be closed at either end. But you can see this is a picture of our data, and it describes 30 pieces of data in a very, very easily understood and represented manner. We can have, when we look at, for instance, frequency polygons, we can see that the shape of the frequency polygon quickly gives us a read. And again, you can see that with our data here, we quickly get a read that most people don't exercise very much. So if you look at the 0, 1, 2, and 3, that's most of our group. And we get very small numbers, 4, 5, 6, and 7. And so this is called a positively skewed frequency polygon. And it simply means that whatever our list of scores are, they tend to be clustered at the bottom. The opposite of that would be if we have a negatively skewed frequency polygon. And in this particular case, we would get a group of people that were, as a group, more likely to exercise in any given week. And so you can quickly see that, hey, most of this group is 4, 5, 6, and there's not that many people at the 1, 2, 3 level. So negatively skewed and positively skewed frequency polygons just gives us a quick picture. When we look at all 30 of these data, all we have to do is look at this and see that our group pretty much is a non-exercising group on the left, or pretty much a more exercising group on the right. Now, another type of descriptive statistics is what we call measures of central tendency. There are 3 of these, and they just give us a sense of average. Again, whether you had 30 pieces of data or 2 million pieces of data, no matter how big or small our amount of data is, a mean or an average, a mean is a kind of average, or a measure of central tendency quickly summarizes and gives us, using one number, a picture of the whole group. And so there's three different types of measures of central tendency, and all of us are familiar with the mean. But again, if we take this question, how many hours do you exercise each week? And let's say in this particular case we had 20 people. So we have 0, we put them in order, 0, 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. So we put them in order from lowest to highest. Okay, let's just say we had that. Now, that's 20 pieces of data. We're looking at a bunch of numbers, not very helpful for us. A measure of central tendency gives us a quick one number average. So, for instance, one measure of central tendency is what we call the mode. And the mode is simply the most frequently occurring score. So we can see when we count our zeros, we count our ones, we count our twos, that 2 is the typical score here. And so the mode is a 2. Now, why would we ever want to use a mode? Well, we use a mode, for instance, let's say we have a bunch of data let's say we wanted to find out, and we took a survey of the students in our college. Well, we would use the mode, for instance, to say the typical student at this college is a woman. The typical student at this college is African American. The typical student at this college is between 18 and 22. The typical student of this college is from New York or from New Jersey or whatever we'd want. So the mode is often used to give us a kind of typical score. And it's a measure of central tendency because it aggregates our data. Another measure of central tendency is what we call the median. And a median is just basically the middle score. So we would simply count up from the bottom, the lowest. We have 20 scores, so we'd count up 10. And we count 10 down from the top. And lo and behold, we see that the middle score falls between the first two from the bottom and the next two. And so the median is that point in our group of scores that falls right in the middle. And we might want to use this, for instance, for income data. If we wanted to know what the typical person or the average person, how much money they make in your town, well, we'd start with the person that makes the least, and we start with and count up to the halfway point, and then again count down to the halfway point from the top, and bingo, the person right in the middle would be the median salary. The third type of measure of central tendency most of us are familiar with, and it's just the mean, and all we do is we add up all of the scores and then we divide by the number. And it's the mean. This is how I would get your mean at the end of the semester when I want to give you a grade. I'm going to add up all your quiz scores and all your test scores and discussion scores and assignment scores and divide by whatever and come up with a mean, 91.3 or whatever, and then I would give you an A-. So measures of central tendency are a descriptive technique. And again, there's strengths and weaknesses to all of these. You can see that here's an example of trying to come up with an average for salary. You can see that a mean in this group of data, so we have two people that make 30,000, we have a bunch that make 40,000, less 50, we have one person that makes 1,420,000. So you can see that if we actually added all these people up and got the salaries, the average person in this particular group would be making $140,000 a year. But that would be kind of inaccurate because there's only 3 people actually out of this whole number that are making more than that. Now the typical mode would underreport the average. So the mode is the most occurring, and so there's the most people sitting on each other's shoulders here that make 40,000, but that wouldn't be quite accurate either. And so in this particular case, the median would be the best measure of central tendency. We would count the number of people, the number of green little people here from the bottom and from the top, and it would give us the most accurate picture. So there are different ways, and there are reasons why we have these three different measures of central tendency. And until you take statistics, or if you've taken statistics, we will go into great more detail on that. Another important type of descriptive statistics is measures of variability. And the easiest and simplest way to calculate this is just the range. We take the lowest score and we subtract it from the highest score, and pretty much that just tells us what the range of scores. Why would we want to know variability in a statistical distribution? Well, just like the measure of central tendency tells us the average or typical score, variability tells us how different our scores are from each other. Imagine you were a teacher and you had two sections of 5th grade math, and you found out that the average math score was a 75 in the year before. Now, you might assume, well, the average in both classes is 75, so both classes are pretty much the same, and I'm going to just teach both classes the same. But imagine your first class, the highest score was an 80 and the lowest score was a 70 and the average was a 75. You would conclude that everybody in that class was pretty much the same in terms of their math skills or math ability. In other words, they have low variability. They're not that different from one another. But let's just assume that the second class, the scores ranged from maybe 20 to 100. Now maybe the average is 75, but that class, man, it's going to be really different, because you have people that are really, really unskilled in math, and you have brainiacs. And if you try and teach that class the same way, the brainiacs are going to be bored, and the people at the low end are going to be completely lost. So you really have two classes that have the same average, but very different in variability. And so variability tells us how different our scores are from each other. A way more complicated way of determining variability, and I'm not going to go into detail here, is what's called standard deviation. And literally, if you want to laugh here, we get the square root of the sum of the square deviations from the mean divided by the number of scores in the distribution. Hey, do that really quickly. And you can see the formula at the bottom there. For our purposes, we don't really care about that. Obviously, this is a way more sophisticated and complicated way of coming up with a measure of variability, and this is what we tend to use most often in statistics. With descriptive statistics, again, we can look here and simply say that here's an example. So the green line here would be our math class that pretty much the lowest score is a 70 and the highest score is an 80, let's say, or something like that. In other words, you can see that most of the scores cluster right around the middle. There's low variability, whereas the red line would be pretty much more variability. In other words, you have maybe the most people are clustered in the middle, but you have more people out on the right and left side of the distribution. And so variability, again, is quite important in statistics, and it's certainly a way which describes our sets of data. Now this is the famous normal curve, and again, I don't want to spend too much time about this, but what I do want you to see is that in a normal curve, and we assume that every single variable that we can study in the world falls on the normal curve. In other words, that most of us tend to fall in the middle of a distribution, and that the farther or more extreme our scores get in any direction, the rarer that is. So if you could look in the middle there and look at 0, if we took something like IQ, most of us fall right in the middle on IQ. That would be 100. The higher your IQ, the higher an IQ goes, the more rare that is. And the lower IQ goes, the rarer that is. 68.26% of the population on any variable tends to fall between 1 standard deviation below and 1 standard deviation above. And again, if you go to 2 standard deviations, it's 96 and change. The normal curve is very important in statistics, and it's just simply the assumption we make that on any variable that we're studying, most people tend to fall somewhere in the middle. In a normal curve, the mean, median, and mode all fall smack on that 0 line. If we did a mean, we'd get right in the middle. The most occurring score, you can see, would be right smack in the middle, and we would have exactly the same amount of scores below 0 as above 0. This is sometimes called the bell curve because it looks like a bell, and I guess you could ring it. With regard to correlation, this is the second aspect of our descriptive statistics. Correlation is basically, you may recall from an earlier lecture, where we look at the relationship between 2 variables. And in this particular case, our 2 variables would be, on the one hand, energy level and whether you're doing yoga or not every day. And so maybe our hypothesis is that people that do yoga every day have higher energy level. And so what we do is we take all of these individual red dots represent the person, and any particular person here would have this energy level and would comply with yoga, and we would represent this in a picture. And if we looked at this, it doesn't really look like there's much of a relationship between these two. In other words, our what we call scatter plot here, or representing our data, doesn't really give us much of an indication that energy level and yoga seems to have any relationship. However, this one kind of does. You can see that the dots go from really they give us a picture of from the upper left to the lower right, and this would simply be a positive this actually would be a negative correlation, in that the more people engage in meditation, the less cigarette smoking they engage in. And so the hypothesis here might be something like smoking is going to decrease with people's increase in meditating. A scatter plot is just a way of, again, representing data in a picture form. And again, if we go back to our coping level here and aerobic exercise, we look at this and it doesn't really seem to present much of a relationship. It's all of the purple dots are all over the place. But if we were to take correlation here, and we were to say, remember, positive correlation would be a situation in which as one variable increases, the other variable increases. And if we go back to our energy level and yoga here, and we looked at it, we'd say, well, there does seem to be a kind of a lower left hand to an upper right hand relationship between these two data. And so this would be a positive correlation, because simply looking at this, we can see that, man, your energy level tends to go up as your yoga compliance goes up. Now, this wouldn't be a perfect, the line in the middle would give us a perfect correlation, but we probably have somewhat of a weak correlation, somewhat of a relationship between yoga on the one hand and energy level on the other. When we look at a negative correlation, because we're going from the upper left-hand corner to the lower right-hand corner, remember, a negative correlation isn't something that's bad. It just means that as one goes up, the other goes down. So in this particular case, as people smoke more, we can see that they're probably meditating less. And the more people meditate, you can see, the lower their smoking tends to go. And again, the red line would represent a perfect negative correlation. We don't have a perfect one, but we do have a relationship here, and that's what correlation does. And statistics tells us in a number between positive 0.1 and negative 0.1, a positive relationship, a positive number would be a positive correlation, and a negative number would be a negative correlation. And so we use statistics to represent a number, to represent these scatter plots. And again, the closer our number is to 0, the less of a relationship we have. The closer our statistic number would be to 1 or -1, the stronger the relationship. So again, I know I've zipped over that pretty quickly, but we're using statistics to represent, describe this scatter plot for us. Remember, correlation does not equal causation. To give you an example on this, does watching violent television cause you to be aggressive? Well, certainly people have wrongly concluded that in the past. But the difficulty here with correlation is we're just looking at the relationship between two variables, and it's easy to ignore when we're focused upon those 2 or 3 variables. All of the other possible variables that may be influencing not only one of those variables, but both of them. This is known as the third variable, or the extraneous variable problem. And in this particular case, watching violent television programs may cause aggression, but on the other hand, maybe aggressive children are just more drawn to watching violent programs. Or maybe there's some genetic cause, or maybe there's some, I mean, there are hundreds of possible things that maybe affect both of those kind of things. I mean, I grew up in a home where we watched almost no television. And, did that mean that I should be not violent at all? Well, I happen to not be a violent person. I don't like watching violence. Now, is it because I watch no violent television? Who knows? There are plenty of people that never saw television at all, and they're violent. So that's the problem with correlation, is we got to always say, well, we have a relationship, say, between yoga and something else, or between meditation and smoking. But we have to be very careful to say that if you meditate more, you're going to smoke less. There may be a relationship, but it's not purely cause and effect. And so here's just a picture of that. Maybe lack of adult supervision causes both, or contributes both, to watching more TV violence and aggressiveness, or any number of other variables here. Now let's talk for just a few minutes about inferential statistics. Inferential statistics is just using various mathematical models, t-tests, and what we call ANOVA. We're not going to talk about those, but to allow us to draw conclusions about our sets of data, to tell us, hey, there's something really going on here, or hey, there may be a small relationship, but not enough for us to be able to say, hey, this particular drug will fight an infection. In psychology, we simply use inferential statistics to tell us that whatever results we have are telling us, on the one hand, that we do have a statistical difference that is significant, or that we may have a difference, but the chances are that our difference is random, that is caused by chance alone, mean that we can't conclude that our study is significant at all. We use inferential statistics to make an inference from a population to a sample. So for instance, let's say I wanted to find out, do research on something. Let's say college students. Well, it's going to be highly time-consuming, expensive for me to test every single college student, even in one country, the United States. So instead of doing that, what I'll do is I'll get a sample of college students. So maybe I'll get a sample of college students, 2,000 college students, and I do the research on 2,000 college students. And what that allows me to do is save a lot of time and money, and I make an inference. Again, on the basis of what I found in the 2,000 college students, can I make conclusions from that small group about the whole group? In other words, can I use the sample to allow me to make judgments about the entire population? That's what inferential statistics should allow us to do. Again, we have all doctors in the United States, but of course, even if I was to survey all doctors in the United States, that doesn't mean I can. That's all doctors in the world. But imagine doing a research statistics or a research study where you had to get all the doctors in one country. Or again, all of the college students. So even if we wanted to do a research study on all of the college students in our college, we might want to say, well, that's going to be kind of inconvenient. It's going to be hard to interview or track down or run down or 2,000, 3,000 college students. So what we're going to do is we're just going to use this particular class as a sample for all of the population of students at our college. And we can do this legitimately, again, by using inferential statistics. We use numbers to judge whether our sample accurately reflects the overall population. That's what we do. Now, the problem, of course, is that there are some things called inferential errors. So, for instance, a type 1 error is pretty much when we conclude that we have significance when we don't. And so the example here would be if we gave a lie detector test and the lie detector test told us that the suspect was lying. In other words, we have significance when he was actually telling the truth. That's called a type 1 error. On the other hand, a type 2 error is that there is something actually, but our statistics tells us there's nothing going on. Now, let me give you a real-life example of this. Let's say that you wanted to find out if you were pregnant, and I'm talking to the women listening to me. So I go ahead and get a pregnancy test at CVS, and it's the urine kind of pregnancy tests. And so those pregnancy tests, again, you have this little kind of thermometer thing, and excuse my language here, but you kind of pee on it, and it tells you if you're pregnant, it turns a certain color, and if you're not pregnant, it turns another color. Okay, so let's say that you are pregnant and you take a pregnancy test, but it tells you you're not pregnant. That would be a type 2 error. In other words, you are pregnant, but your statistical research told you you're not. On the other hand, a type 1 error would be that if, let's say, you're not pregnant, but you take the pregnancy test and it tells you you're pregnant and you start freaking out, and indeed you're not. So clearly, research always has to grapple with the fact that if we are making an inference from a sample about a population, since we're not taking data from the whole population, but we're making an inference, we always have to remember we can make a type 1 or type 2 error, and in both cases, our research statistics are wrong. Now, how to avoid these errors? Well, the more representative our sample is of the whole population, the less likely we are to make these errors. So if at our college, 70% of the college students at this college are women, then if we have 70% of our sample as women, we are less likely to make that error. Okay? Clearly, if our sample is less variable as opposed to more variable, in other words, it's hard to control for this, but if the answers from our population tend to be clustered or similar, we are, as opposed to dissimilar, we are likely to make less errors. And finally, the more people we have in our sample. So if we have 2,300 students in our college, and we took a sample of 300 of them, we are way less likely to make type 1 and type 2 errors as opposed to if we took a sample of 10 of them. So the more people in our sample, the better. And then what we do is we simply use various statistical formula. We do this all by computer now. We plug our data in and it tells us, hey, bingo, you have something, or non-bingo, you don't have something. Now, as you read in your textbook, or will read in your textbook, there's different types of methodology. One is a longitudinal study. In a longitudinal study, we follow one group of people for a long period of time. And that has strengths and weaknesses. Let's say we wanted to find out what happens from kindergarten to 12th grade. Let's say we took 5 schools and we wanted to know, does self-esteem stay the same? Does it go up? Does it go down? And so we followed these people for 13 years. Well, the advantage of longitudinal studies that is that our subjects stay the same. We get actual data in real time. But the problem, of course, is that it's going to take 13 years for us to get our results. So sometimes what we'll do is we'll do cross-sectional studies. We'll go to 5 different schools and we'll test everybody in the schools, all the kindergartners, first graders, second graders, third graders, fourth graders, fifth graders, sixth graders, and so on and so forth up to 12th graders. And we'll assume that the 12th grade score that we get would be similar to if we followed people for 13 years and we compare the data. Now, the strength about that is we get our data right away, but of course the weakness is that the 12th graders are actually different people than the third graders. Methodology is pretty important. With these studies, we are able to do one as opposed to the other, and by doing this, embrace the strengths of one methodology, avoid the weaknesses, or vice versa. And depending on what we're studying, we would certainly want to use one or the other here. Thank you for listening, and see you in the next